Okay, so let's finish up the implementation of Gaussian mixture models. So we're going to use exact the same data that we have shown that in the k-means. So we have 5 cluster here, and each cluster is actually has different size. The densities will be different as well. So this is the data set we are going to work with and apply the Gaussian mixture models. So here is the same. We're using the k-means plus to set up the initial condition. I'm not going to repeat what we already done. This is nothing but just start and get my initial conditions. So this is basically getting, and say we already know this cluster, and the number of clusters that we need is 5. So this k equal to 5. Then we create the centroids for this 5 and for this initial guess. And of course, you can use this and the initial guess randomly. But in general, if you're using k-means plus to set up initialization, that will, in general, will be likely to have a better result. So these so the next part will be the mean and the mean functions for Gaussian mixtures. It has a bunch of separate functions. For example, this is just initialization. So we want to initialize the weight, which is pi. So this is the initialized weight that we have, like uniform initialization. The initialization is 1 over k. And this is the initialized weight for the posterior distributions. This is again, that will be 1 over k. So here is the initial mu. This is basically the position of centroid for each cluster. We already used the k-means plus as our initialization for the mu. For the sigma is we are using the covariance matrix of this k Gaussians we already have. So basically, we take the whole data of X and that would be and we calculate the covariance of the whole data set. That will be my sigma. So this is my initialization. Very simple. The slightly more complicated part is we are going to take this input of centroid, which is initialized from k-means plus. All right. So let me enlarge things a little bit. And also, okay, so, and right here, and we know in the E step, that's basically compute the posterior probabilities for each data point with respect to each cluster. So basically the output will be my weight. Weight is the 5 matrix we have talked about. So this is the size of m is n by k. So this is basically, and the probability zi equal to c, conditional on the x of I. So right here, and basically what we do is we create this n by k matrix to denoting the probability at like each point with respect to the cluster. So we first calculate the corresponding likelihood. So this is, the actual distribution right here. So here we just make things a little bit easier. We just use the SciPy function on the multivariate normal to calculate the PDF, directly for each cluster. So this is mu of I and sigma of I. So, and the mu here is actually a list of the mu, and the sigma here is a list of sigma. So for and for k different clusters. So if we and want to assess the corresponding mean, that will be mu of I, and corresponding covariance will be sigma of I. Then you actually calculate the likelihood, and you put this likelihood and to the like ith column right here. So this will be your likelihood function. So, and your likelihood function will be like n by k. Here we just apply the whole data matrix here. So this whole data matrix is, if you apply the matrix instead of one array, they will just calculate for each row, and they will treat each row as one data entries, and then then they are going to plug in into this PDF and then calculate the likelihood for each of the data entries from 1 to the n. Then the output will give you a whole column of this pop and the likelihood, and that will be the likelihood corresponding to to the ith cluster. So that's why it will be plugging back into the ith column. Then we need to multiply the pi, right? So this is something that we miss out, which is the pi and the pi c. So we multiply pi here. We are using, the same trick of the broadcast of the and the variables. Then so this is basically the denominator, because for each let me think about this. For each row we have to sum up to be 1, right? Because that will be my posterior distribution. So that means you need to so you need to like divide it by divided by the norm of each sum of each rows. So this is basically what we are doing for the denominator, and to ensure each row that you got for the posterior distributions sum to be 1. So this weight and will be my phi and phi matrices. And so this is my E step. So E step is basically if we are giving the pi mu sigma the weight being constant, then we update for the phi. Phi is my so posterior distributions. So this is the only and for the E step. And also once we have this weight, we can make prediction for each and the data entries. This data belongs to the cluster with the maximum probabilities. So that means we will return this index. So basically, if we find out this weight, and which is posterior distributions, and what we actually do is we just return the argmax of the weight and for each row. So for each row, you're going to find out the corresponding indexes. So that means that we can set with x is equal to 1. At the end, we are going to output a columns of so a vector of size of n, which is give you the prediction of and the corresponding clusters. Okay, so here the M step is basically we holding this phi, the weight as a constant. Then we're going to update mu sigma pi, right? So this is basically the opposite. I mean, the philosophy is still very similar, as you can think of everything being alternating as optimization. But in M and step that you're going to hold the phi being constant and update mu sigma and pi. So what you do is you are going to, so the mean of the sum of the probability of all the data point where the one cluster is the new updated probability of the cluster pi. Right. So basically what you do is you take the mean of the weight so that will be column wise. So basically we know each row has to be sum of 1 for this phi. But from the formula right here, we are actually trying to sum and fix the column and sum for each column right here. Then you take the average with that. So this will be nothing but you are taking the mean for each column, and you do this update for mu. You do this update for sigma. For the mu update, this is the same thing, and this will be x times of the weight I. So weight I is basically the ith columns of this phi. Then you like x times of an ith column and divide by the total weight, and you basically average out. That will be the ith update for the mu. So that will be the ith and the mu for the ith cluster. Then you do the same thing for the sigma here. But the difference is, it's much easier. And what you can do is you just do the weight for and using this like covariance function here. So for the covariance function here, you can set the weight as being and weight I divided by the total weight. So this will be the weight that you're going to apply for each sigma here, and for each data entry here. And also, if we just using the covariance here, this will give you, and we're divided by 1 over n minus 1. So if you assign the bias to be true, that means you are going to, and the one way is when they calculate this will, and just simply be 1 over n. So, and this will be the empirical, the MLE for the covariance matrices, right? So, I mean, this is important, but if you don't do this, you are going to just divide it by n minus 1. That's not my MLE estimator. So, and we are getting this pi update, a mu update, and sigma update. So this is my M step. All right, so the mean function is right here. So we know this has and step 1, step 2, step 3. I think I switched the number a little bit. So basically the step 1 is like initialize the parameters like weight, like pi, like mu, like sigma for all of the Gaussian that we have. It's all being in like this initialization function here. Step 2, step 3 that we are going to iterate with E step and as M step. We iterate over this maximum iteration numbers. So basically right here, so this is the E step. It's the like we iterate through to update the value of the posterior distributions. Then we have and we assign my pi and to the old pi and mu and to the old mu, and just to have some comparison later on. On step 3, we're going to take the M step, which is and update the value of mu sigma pi as we have the shift of the clusters. And we can using this and we can use the same idea that we had before in the k-means to see what is the distance between the current mu and old mu's, and to see whether they have been updated or not. So this will be the distance between my previous mu and the current mu for all different and all k different clusters. If the distance that we got is like sum of distance that we got is less than some threshold, then I will stop. So basically they don't change too much, then I will stop. And otherwise they will continue these iterations, right? So at the end, as once they break these iterations, I'm going to using the final pi mu sigma as my optimal parameter to make the predictions of the member of cluster for each data point in X's. Okay, then I like output my mu and doing some plotting here. Okay, so this is very straightforward, and you can see how I'm implement this E and EM algorithm from scratch. So, and this is the result that you're getting here. I want to remind you, this is quite difficult data set. In general, it will be very hard to classify for k-means. So you can see this is my initial condition I'm with the k-means plus and initialization. We have 1 here, 1 here, 1 here, 1 here, 1 here. So to ensure like all these initial analyzation to have to be as furthest as possible, and they start to like iterate gradually. And you can see so initially we have one cluster here, another cluster here, like tiny cluster here, was 1, 2, 3, 4, 5, and 5 different clusters. And obviously this is really bad, but through this EM and algorithm, and they start to move and gradually. But you can see this is doing not very good job right now. We are like basically splitting this and the large ellipse and ellipse into 2 parts. But the beauty of this EM algorithm is eventually they start to work through and find out, okay, they are moving back into and gradually moving back and trying to take over these clusters. And gradually at about 7, 8 iterations of EM algorithm, the update of the distance is less than 7 times 10 to the 5. So this is like we reach the threshold and our iteration stops. But you can see in this cases, it perfectly separate these clusters into 5 different clusters. Unlike the k-means that we had, this and Gaussian mixture models is successfully finding out these 5 clusters without any problems. And of course, this is also depends on the initial condition that we have. Sometimes with the different initial condition, it might not work very well. But compared with the k-means, k-means is very, very unlikely you can and a cluster data in the way that you want it. But in the Gaussian mixtures, it's more likely you can classify into these correct 5 clusters, right? So this is much, much better. And also, just from like our M step here, our sigma here, I forgot to mention, if we just using the covariance matrix with this weight of each of data and introduce the bias, which is 1 over n, this sigma is automatically satisfy the positive definite properties. So we don't need to worry about the constraints of our optimization. So that's the beauty of EM algorithm. The point of an EM algorithm is we don't actually need to worry about the constraint, and this constraint just automatically satisfy when we actually apply this EM algorithms, unlike the gradient descent methods. All right, so so you can see this after like, and of course, compared to k-means, it takes quite significant longer and the iterations, but it did actually work very well. We can also do some illustration with the Gaussian mixtures to apply these points on the like 2D plane. So we have done this things in the k-means. So like and basically we want to like construct the like Voronoi cell. This 2D plane. So this is actually the plot for this and the decision boundaries. So if we actually plot that with this 5 point, we can see this is actually our decision boundaries to separate and data into 5 different clusters. So we have, and you can see like one cluster look like it and this. So what does that actually mean? If you are giving a new point in this 2D plane, say right here, I will classify this as like orange right here, because in terms of distance to this and to this and that will be closer to this and the clusters compared to other 4 clusters, right? So this is basically the idea and how they build the and the decision boundaries in this 2D plane. They build this like and the Voronoi cells and to partition this whole spaces into 5 different regions. But you can see this, and from this you can see this like boundary lines is no longer straight lines. If you remember, go back to k-means, you will find out and the boundary is separated by straight lines in general. But in this case, and we can show you later on, this is being separated by a quadratic curve, right? So, and this is the and you can see some like good ideas and what you can pop up here, but this just give you some good illustrations on that. Making the predictions. So we can also plot this this PDF of and a PDF of this 5 Gaussian mixtures. You can see we have like 5 different peaks. We have 3 peaks looks quite similar. These 2 peaks look similar here. And we can also plot the counterplot of this PDF. You can see this is quite nicely illustrated with these 5 peaks and this counterplot of the whole densities. Right, so it actually correctly identify we have like 5 clusters right here, and also these 2 clusters are very close to each other. It's kind of like merging to one, but it's not really merging to one. So this is kind of like very nice way to illustrate and the connections between like different clusters. All right, so last is also, but not the least, is you can use this whole idea to calculate the negative log likelihood for k equal to 5. So what you can do is basically what we do is we get this likelihood function. We already and did that. I mean in the so when we calculate the posterior distributions, but instead of you calculate posterior distributions, you can actually and multiply the dot and multiply the pi, then apply the log functions, then you can sum them together. So this is basically the log likelihood. And if you plus and put the minus sign, that becomes negative log likelihood. So basically, and this will be your and the likelihood matrix, but you're going to take the logarithm and sum the whole matrix up into one scalar. That scalar, there will be your log likelihood values. Okay, so from here you find out, this negative log likelihood is about 5,005, like 6,574, and you can try with different in a situation to see whether, and you can using this as a like golden standard to see and which clustering will give you like and minimized and a negative log likelihood. It's like distortion value that you had in the k-means. But in the Gaussian mixture models, the goal is you want to so minimize negative log likelihood instead. So this is something that you can be used. And also in the homework, you're going to actually use this piece of code to turn this into a function. And then later on, there are a bunch of other tricks that can be applied to work on various other problems. For example, in Gaussian mixture models, I didn't tell you how to choose the optimal K. In fact, there are some like methods that you can work out and to using some like an additional like penalties to actually to find out the best and optimized case in these situations. Unlike the k-means, we have elbow methods. In Gaussian mixture models, we usually use different methods as well. So in the next lecture, we're going to talk about that homework in a little bit detail, and particularly how to find the optimal case. All right, so that's all.